Okay, good afternoon, everyone. Thank you for attending the Building Science 101 webinar today. This webinar will be recorded and the recording will be sent out to all attendees. If there are any issues with audio, please write me in the chat. My name is Erica DeBello and I'm a project manager for Noresco. This series is sponsored by the Colorado Energy Office with training materials created by Tank Incorporated. Robbie and I have been working with the Colorado Energy Office to provide trainings just like this one. Here's a list of the trainings that are offered in this series over the next few months. There will be a link sent out in a follow-up email if you'd like to register for any other webinars. Also, we are offering tailored group trainings or technical assistance for jurisdictions that are updating I-codes. And then in addition to that, we've also created a toolkit that reviews cost implications of changing code cycles, the benefits and other compliance resources. And then included in that code adoption toolkit is a troubleshooting guide that helps to clarify I-code conflicts, alignments, and paths of compliance. Both of these resources can be accessed on the Colorado Energy Office's website. So throughout this webinar, we do want to encourage questions. So please use the Q&A function, and I'll let our presenter know at the end of the presentation. The chat window can also be used, but mainly to chat amongst participants. So please use the Q&A function if you'd like to ask a question. There is also the ability to raise your hand at the end of the presentation, and then I can unmute you and you can ask your question directly to Robbie. Lastly, there will be a survey window that pops up following the webinar. Please take a minute to provide feedback so we can continue to improve on these webinars. Today's presenter is Robbie Schwartz. Robbie has founded the Tank Incorporated to be a practical building think tank to do research, education, and work with builders to ensure that their homes not only comply with codes and programs, but also perform. At Tank, they strive to use what they learn from the field work to affect meaningful change in the construction industry. So with that, I'll let you take it from here, Robbie. Go ahead and stop sharing my screen so you can take control.
There we go. Welcome everybody to our session today, which is on building science, introduction to building science for residential mechanical contractors. I am going to stop sharing my video so that everybody can concentrate on the slides. And then when we get to the Q&A section, we will go back to using video there as well. So thanks again, and please don't hesitate to throw out a question into the Q&A pane, and we'll get to those questions at the end here. Today, we're going to be talking about why we're going to be talking about specifically HVAC systems today and the building science around that. We'll be talking about the heat load calculation, why we need to look at air and how air actually works and moves inside our houses. And then this notion of, is it there and does it work, and what assumptions we're ultimately making in when we're doing our HVAC calculations from a building science perspective. So really why we're having this conversation is that our HVAC systems will not work unless our envelope, our building envelope works. The reality is that the energy use of our homes is dictated by how well we implement the building thermal envelope in our homes. And if we're not implementing those envelopes well, we're not going to be able to mitigate or reduce the amount of energy that is being used in those homes. And if we're not taking that into account during the design process of our HVAC systems, we're going to have problems as well. So this notion of, is it there and does it work, comes into account when we make assumptions about what our building envelope is going to be, and if we've executed that properly or not, to ensure that we have a envelope that will perform, that meets and matches what our HVAC design process is is assuming in essence. So when we look at a simplified design schematic of the construction process, we see from design to project closeout, these are kind of the steps that we go through when we're building a home. In the same way, we can look at the design process for an HVAC system. And when we try to match the two of them, we see that the design process for the HVAC system happens in the pre-construction cycle of the construction of a home, which means that the HVAC designer is using a fair number of assumptions about how that house will actually be built. You know, will that house be using blown insulation or bat insulation, for example? And ultimately, what's the R value that they're using? And will that R value be carried out and installed in such a way that it will actually perform that way? Same thing with air tightness. We're assuming the house is going to be tight. Will that house actually be tight during the construction process? And how does that ultimately impact our design? Our design process can be boiled down into a relatively simple system of 3 steps. The first step is calculating the heating and cooling loads for the house. That's that manual J portion of the equation. The second step is selecting the equipment with the capacity to meet the loads. That's the manual S portion of the calculation. And then the manual D portion of the calculation is designing the actual duct system that will deliver the air to the rooms that we ultimately need there to create comfort and durability in our homes. Now, how is this happening in relationship to the building envelope? Well, that manual J portion, the load portion, is assuming the R values and U values around the building envelope so that we can meet our ultimate goal of consistent temperatures around the building envelope from room to room and floor to floor. The reality out there, however, is that we're making assumptions that aren't getting carried out, or we're making assumptions that the building envelope won't be as good as it actually turns out to be. So we're oversizing systems there. So we get this notion of the ability of systems to be oversized because our building envelope is not good enough, or it could be undersized because we are, well, it would be oversized because we're assuming that our envelope's not going to be good enough, and it can be undersized because the envelope turns out not to be good enough. Where we really want to get is that well-insulated house with the right-sized HVAC system, and we have both working in coordination with each other. So in order to get that, we need to think about the building science a little bit and how we're going to ultimately get that. And we need to take into account some new aspects of inspection and verification to ensure that we're getting what we inspect and expect there. So from a manual J heat load calculation point of view, 3 pieces of information are needed to be taken into account. We need to know the R value. We need to know the area of the assembly that the energy is moving through. And we need to know the temperature difference, or delta T, across that assembly. Now, the delta T portion of that delta T is given to us by the IECC. It says what the interior design conditions have to be, and those are input into our manual J software, for example, here with RightSoft. And the outside design temperatures need to be given to us by the jurisdiction directly. So in most cases, the jurisdiction is doing that. But when we have that information, we can plug it into a formula. And this is what's happening behind the scenes in the manual J heat load calculation. So BTU hours equal the U value of the assembly, or the U value is just the reciprocal of the R value, times the area, times the delta T temperature difference across that assembly. So if I have this house that is 20 by 20 with 10-foot walls, and I'm just trying to find out what's the heat loss or heat gain through those walls if they're insulated to an R20, I would run it through this equation, and I would see that 840 BTUs per hour are going through the walls if I have a temperature difference of 21 degrees across that wall assembly. And I can also see that almost a little over 20,000 BTUs per day are moving through that assembly. So this is in essence what the manual J process is doing. It's adding up all of the building assemblies that have heat loss or a temperature difference across them to the ambient outdoors. And it's giving us a total BTU load for that house. So let's break it down in a little bit more detail here. When we do that, we have to think about the first law of thermodynamics, which basically says that energy can't be created or destroyed. It's just changing phases or states during its movement from place to place. So if we take a furnace, for example, the energy in equals the energy out plus whatever waste energy is there. So if I have a 100,000 BTU furnace and it's a 90% efficient furnace, then 90,000 BTUs will be the output of that furnace, and 10,000 BTUs will be the waste of that furnace, going up with flue gases to the outside ambient air. So the equation is actually balanced here. We have 100,000 BTUs on each side of that equation. However, 10,000 of those BTUs are not useful for heating or cooling the house. In this case, heating the house here. Now, the second law of thermodynamics says that heat moves from high temperature regions to low temperature regions, basically from hot to cold, or from higher concentrations to lower concentrations. It can't flow in the other direction unless you add additional energy to the equation there. And as we saw before, no reaction is 100% complete. And this notion of energy transfer, as it happens more and more energy is wasted in this equation here. So we want to be as efficient as we can in that first transfer of energy from gas to air, for example, in that 90% furnace, because if we are trying to do it a second or third time, we're going to get more and more waste energy. So the big takeaway from that is that this heat transfer mechanism here is always from warm objects to colder objects, or from higher concentrations to lower concentrations. So when we start talking about temperature and heat, we see that exemplified again here. Heat is a form of energy, and heat is measured by how that energy is transferred from one system to another system. So for example, how the energy is moving from the dog's body to the ice cubes to ultimately melt those ice cubes here. Temperature is a measure of the internal energy of a system, or a measurement of how fast the actual molecules within that system are moving there. That's what's getting measured by a thermometer. It is the thermal energy of that system that increases the random motion of these molecules that increases the thermometer temperature up and down here. So if we're moving the energy faster in that system, we have more energy in that system, the energy is going to go up, or the thermometer is going to go up. If we're slowing it down, then the thermometer energy is moving, the thermometer is moving down in that dial there. Heat transfer is the exchange of thermal energy between these objects. And we have to know that energy, that you basically just have to have more energy than the object that it's being transferred to in order for that energy to be transferred to. And that's why a heat pump works on a cold winter day, for example. We have this whole host of new air source heat pumps, for example, that can get energy out of air that's close to freezing out there, because there's still energy in that air, and it just has to be more than the surface that you're trying to transfer that energy to in order for energy to move there. That can be described by this notion of temperature difference. So in this case, I have a large delta T, or temperature difference, across this building envelope. I have 58 degrees temperature difference. So there's going to be a lot of energy that's moving from, or wanting to move anyway, from inside the conditioned envelope of this house to outside. Now, if I was closer to 60, let's say I was 65 degrees outside the house, there would still be energy transfer from inside to outside. It would just be less energy transfer. So energy is always trying to equalize itself, to create equilibrium, to have a consistent, constant temperature. If you were measuring that energy with a thermometer, then it would want to equalize itself on each side of the boundary condition, which would be, in this case, the thermal envelope of the house here. Again, the IECC tells us what that interior design condition is for HVAC calculations, and most jurisdictions tell you what the outdoor design condition, because that's a climatic issue that changes in each jurisdiction that we're working in here. So just to recap, we know that energy is the flow from higher concentrations to lower concentrations, and that the greater the delta T, or the higher the delta T, the more heat or air will want to escape or enter the building from the direction that the higher energy is. In the wintertime, it's usually higher inside than outside. So the energy is moving from inside our homes to outside. In the summertime conditions, generally the energy is higher outside or greater outside. So it's moving from outside to inside in that equation there. The next thing we need to talk about is this notion of sensible and latent heat, and these two versions of heat. So sensible and latent heat describe energy that's released or absorbed by a substance, but it's done a little bit differently. Sensible heat is related to the change in temperature that is equated with no change in state or phase. Phase, when we're talking about phase change or state change, we're talking about a liquid becoming a solid or a liquid becoming a gas, for example. That's a change in state. And that's ultimately what's described by latent heat. Latent heat is directly related to this change of state from a solid to a liquid or to a gas, for example, like this tea kettle here. That additional energy that pushes that molecule out of its steady state or in its liquid form into its gas form, or from a solid to a liquid as well. So diving a little bit more deeply into sensible heat, we see that sensible heat, again, is that energy that is sensed by a thermometer and can be measured by a thermometer. Heat carried by air is measured by that thermometer. And this is the type of energy that's ultimately described in our heat load calculations. So we really need to be able to take into account the amount of energy that's coming into our homes by sunlight, how much the insulation of our thermal envelope is resisting the flow of energy from inside to outside or from outside to inside, how much energy is being carried by air coming in and out of our homes, how much energy is being contributed to that house by lighting, appliances, and occupants as well. All these things are described in that heat load calculation, and all of these things are considered sensible heat here. Now, sensible heat moves or transfers from body to body by conduction, convection, and radiant energy movement. And this is what we call the heat transfer mechanisms of sensible heat. And the other interesting thing about sensible heat and conduction, convection, and radiation inside our homes is that it's happening simultaneously. Energy is moving around our homes by the heat transfer mechanisms of conduction, convection, and radiation simultaneously and in different directions in our homes, but always from higher concentrations to lower concentrations. Conduction is this measurement of energy that's moving or conducting directly through objects. So directly through our wall assemblies, or in this case, directly through a metal pipe or piece of metal from higher concentrations where the flame is to lower concentrations where this person's hand is. We see it in our houses where we get greater conduction through wood and faster conduction through wood than we do through the building assembly that's actually insulated, in this case to an R23. We see that resistance, or the R value, is greater with an R23 than it is at the stud level, which is basically R1 per inch, or an R6 for 2x6 stud there. Again, it's largely dependent on the temperature difference across that assembly, but this is the measurement of energy that's moving directly through the assembly, or what we call conducting through the assembly. Next, we have convection. This is energy that's moving with a fluid like air or water. You can see convection happening inside a teapot or inside a building with air movement that's carrying energy, either air that's cooling and falling to the floor, or air that's warming and rising to the ceiling, for example. That's convection that's happening. Our weather is all convective energy that's moving around our planet here. And we see that convective energy can move air around our houses, and which we're counting on with forced air systems. It can also move energy out of our houses if we have poorly insulated cavities and convective loops that are happening inside our cavities. That's taking energy from the warm side of our assembly to the cold side of our assembly, and ultimately bypassing the insulation that's inside that assembly. So when we're talking about the effectiveness of the insulation to do its job, it's often and really critical to ensure that that insulation is installed properly inside the cavity. So this was a little test situation that was created where we have a box that has 4 cavities that are insulated differently. And it would be interesting to see if you could guess which cavity do you think is performing the best, and which is performing the worst, and which cavity has the most insulation or not. So to break that down, these are the 4 cavities and the type of insulation that's in each of the cavities. Let's see, make your guess now, and I'll tell you which one is which. So cavity 1 is an R11 bat that's installed perfectly to a grade 1 or to the requirements of code. And you see that there's little to no heat loss through that assembly, because the R11 bat is doing its job. The R19 bat, however, has gaps at the top of the assembly. So it hasn't been installed well. It hasn't been installed to that grade 1 or to the requirements of the code, the energy code. And therefore we have a significant amount of heat loss at the top of that cavity where the gap has been located. Cavity 3 is an R13 bat. It's been installed pretty well, but not perfectly. You see some gaps at the top and some bypasses around that insulation. And cavity 4 is an R0. There's no insulation in that cavity at all there. So this, again, harps back to the beginning of the presentation, where we've got a cavity, or we've got an assumption that our house might be insulated to an R19, but it's very dependent on how well that R19 bat has been installed to ensure that we're actually getting that resistance to the flow of energy there. And therefore our system might be undersized if we assume that we're getting an R19 and we're not actually getting that R19 in that cavity. Jumping back into radiant loss here, radiant heat loss or transfer is when energy is moving through open spaces from higher temperature objects to lower temperature objects. This is best explained by thinking about the sun's energy radiating through space to the earth, or when you're standing by a campfire on a cold evening and that heat radiating through the space between the fire and the people sitting around the fire. Now, radiant energy is most often used to our advantage or disadvantage with regards to cooling dominated climates and the use or non-use of radiant barriers. Now, we're not going to go into radiant barriers in great depth here, but the idea of a radiant barrier is that it has the ability to reflect and also radiate energy, so that less of the energy from the sun is going into the attic and then ultimately into the home, and therefore you're reducing your cooling load on that house. As I said before, this notion of thermal transmission, where things are happening simultaneously, is happening constantly inside of our houses. So we've got conduction, convection, and radiant heat flow moving energy in and out of our houses simultaneously. So if we understand and can break down conduction, convection, and radiant energy, we might be able to determine which is the biggest driver in any situation. And this happens a lot when you're doing warranty work or kind of forensics on a house to determine if that house, why this particular room is cold, why it's not heating properly. Is it a thermal envelope issue? Is it a HVAC issue? Which is the biggest driver, conduction, convection, or radiant loss in that particular room or house there? Now, remember, we also have this latent heat part of the equation that we need to think about. So latent heat is the energy released or absorbed by that substance when it's changing state or phase. So when it's going from a liquid to a gas or from a solid to a liquid, for example, there's additional energy that has to be added to the equation to get it to change, to actually make that phase change there. So when we think about this latent energy transfer and the mechanisms that are described in that heat transfer in latent heat, we think about evaporation, condensation, freezing, and melting of materials there. Now, unlike sensible heat, this is not happening simultaneously. This happens one at a time. So you have to go from evaporation to condensation, or from a solid, a liquid to freezing there. And that happens, in sequence, not simultaneously there. Evaporation and condensation is this notion that latent heat is this energy that's required to overcome those bonds of the liquid water, if we're taking water as the example. So water, the H2O molecule, is bonded very securely. So some additional energy needs to be added to that to get that molecule to escape from the water into its vapor state there. So the liquid absorbs heat when it changes from a liquid to a gas ultimately here. In the same way, condensation is taking it, the gas is giving off heat though, in this part of the equation, to change it from the gas to the liquid, back to a liquid, to create condensation on a window pane, for example here. But in either case, there is a additional influx of energy that is moving it and making it change state here. So when we have liquid that's boiling, we see from a sensible perspective that liquid is reaching 212 degrees, but it's not, the liquid portion is not changing temperature above 212 degrees. It's a constant 212 degrees. The additional energy that's moved into that equation to get it into its gas stage, that is the latent heat. And that I think they probably can measure it, but we know that latent heat is actually moving and working and transferring because the molecule is changing from its liquid state to its gas state here. Now, another interesting thing is that this latent heat cycle is what's happening in an AC system. And we need to understand that AC system is a closed loop system. So at the compressor, we start with this low pressure gas that's going through the compressor to make this high pressure gas. And that high pressure gas ultimately goes to the condenser, where it's getting condensed into a liquid. So it's changing state here. And as it's changing state, we see energy that's being transferred. The liquid moves to the expansion valve ultimately as a high pressure liquid. And then that expansion valve changes it to a low pressure where it ends up going to the evaporator and changing state again at the evaporator here. So we see this refrigerant cycle is completely dependent on a latent heat transfer, and it's all happening within a closed loop system. So that means that the refrigerant is locked within the piping system of our AC cycle here, and it's going through this latent heat change to take energy from inside our house and move that energy outside of our house. And then when you get to a heat pump, you have the ability to change the direction of this refrigerant cycle. So you can move energy from outside the house to inside the house here. However, when we are trying to cool houses and HVAC contractors are trying to design HVAC systems, which includes the air conditioning side of the equation, we have this latent heat that is outside of that closed loop that we need to think about. And that latent heat is ultimately trapped within the water molecules that are inside the air, which is described by relative humidity. So relative humidity is the amount of moisture that's held by air compared to the maximum amount possible. When we get 100% saturation, that's when the water molecule actually comes out of the air and sticks to a surface like this glass pane here. So when we're talking about humidity, I like to think about the air that the humidity is being held in as a towel. And you can think of a towel and the size of that towel as a function of how much humidity can be held within that air molecule. So warmer air would be a larger towel and colder air would be a smaller towel. And in that, if you think of it in that way, you can think about the percentage of air, the percentage of moisture that's held within that air as a towel that can hold more or less water here. So absolute humidity is how much moisture is in the air by weight, but relative humidity is the amount of water vapor that's present as a percentage of the total amount that it can hold. So if I have a larger towel, I would be at 100% relative humidity, and that towel could not hold any more moisture, and that moisture would start dripping off of that towel and onto the floor. Whereas if I had a smaller towel at 28% relative humidity, or if I had that same size towel at 28% relative humidity, it would just be able to absorb that moisture in that towel and not come out. But there would still be moisture in the towel or in the air that we are surrounded by. So the latent heat removal cycle of HVAC systems and HVAC designers this is what they're taking into account. This is the quantity of moisture in the air, the relative humidity that we have to take into account. The latent heat removed through condensation of warm, humid air passing over the evaporative coil inside of our houses is one additional benefit of the air conditioning cycle, is that we can, in essence, slightly dehumidify the air inside of those houses. Now, the problem occurs when we've got the sensible temperature is being met, but we still have a lot of latent load inside that house. This happens a lot in humid climates where we've got a swing season, for example, and we don't need to cool the air that much, the sensible cooling of that air that much to create comfort from a sensible thermometer perspective, but we still have a lot of relative humidity inside that air that we need to get out. And so there are issues there that an HVAC contractor needs to deal with to properly size the equipment to try to deal as best they can with the latent load that's the relative humidity that's in those humid climates. but also understand that you probably aren't going to be able to deal with all of those loads, and therefore you might have to also put in a dehumidification system that can specifically deal with the humidity inside that house and inside that particular climate zone that you're dealing with there. Now, the next thing we need to think about is that, the latent and sensible loads and how they deal with human comfort. Another aspect of that human comfort equation is this notion of mean radiant temperature. And mean radiant temperature is a description of the temperature of the things that surrounding our body. And if that temperature is lower than our body, then our body temperature will actually radiate to that colder surface. So for example, this person's body's temperature is around 98.5 or 6, and therefore it's going to radiate to the cold surface temperature of this window here. So the 6 variables of comfort, we can control some of them. We can control air temperature, and we can get better control of the relative humidity and air movement in our houses. And we can better control the mean radiant temperature around us as well by choosing better windows and better thermal envelope insulation levels, better house tightness, all these different things we have some level of ability to control. But the clothes that people choose to wear, we don't have a lot of control over, and people's metabolic rate, we don't have a lot of control over. We know that women's metabolic rate and men's metabolic rate are different, so people feel comfortable in different situations within their house. So again, the HVAC contractor is looking at trying to figure out how heat flow is moving, how much heat flow and heat load that house has in order to create comfort within that house. And it's a very difficult thing to manage all these things simultaneously, these variables of human comfort simultaneously. The next thing we need to think about is air movement. So we've talked about the kind of the thermal envelope, R value perspective, the energy moving through those, through that building thermal envelope from a conduction, convection, or radiant heat flow perspective, and also from evaporation, condensation perspective as well. But energy also moves through our houses by convection. And convection is basically how we're describing air movement around our house. Now, the thing that I like to think about air and reference air movement to is a freight train. I like to think about air as a freight train because a freight train is moving cargo from point A to point B. And air is also moving cargo. Air's cargo is energy, it's moisture, it's pollutants, and it's often taking that energy, moisture, and pollutants from inside our house to outside our house, or from outside our house to inside our house. And we need to figure out how we're going to get control and predictability of that airflow and the cargo that that air is carrying. And so we get this question quite often, can our houses be too tight? And the reality is that the answer is no, our houses can't be too tight because we're trying to gain control and predictability of that airflow and the cargo that that air is carrying, the heat, the moisture, and the pollutants there. So the real question that we should be asking, because this is the wrong question, is are our houses underventilated? And the reality is that they are underventilated because we want to build our houses as tight as we possibly can to gain control and predictability of airflow in our houses, because they can cause so many problems in our homes, which means that we need to ventilate our houses properly because it is a way to have control of the air moving in and out of our houses, as we'll see here in a few minutes. So again, the whole issue is control of the airflow moving in and out of our houses and predictability of the airflow moving in and out of our houses. So just like when I go get a Big Mac sandwich at McDonald's in Denver or San Francisco or Paris, France, or New York, I know, and it's very predictable, exactly what I'm going to get when I get that Big Mac sandwich. And I know how I'm going to feel after I eat that Big Mac sandwich. So that's the level of predictability that we need in our houses. And the only way to get that control and predictability is to build our houses tight. So that means that we need to get better control of the holes and the pressures inside our houses, because holes and pressure are the two things that are needed for air to move through our building assemblies here. And we're doing a better job of sealing up the holes in our houses, but let's try to understand the issue of these two things needing both the hole and the pressure in order for air to move. So imagine that this balloon is a house and that the rubber membrane of the balloon defines the building envelope of our house. If I have no holes in that rubber membrane, or if I have no holes in my building envelope, then air won't move from one side to the other side of this defined boundary that we've created. However, if I introduce a hole, if I untie the string that is holding this balloon together, then the pressure difference across the building envelope or across the rubber membrane changes. I have greater pressure outside than I have inside this balloon or my building envelope here. And therefore, the outside pressure is going to push inward, and that air is going to come out of the hole, and that balloon is going to fly away, right? So what we've learned here is that I need a hole and a pressure difference across that hole for air to move. And also what we know is that air in equals air out. If we measure air in cubic feet, we know that if 1 cubic foot goes into our house, then 1 cubic foot of air must go out of our house. Or if 1 cubic foot of air goes out of our house, then 1 cubic foot of air must go into our house. So we know that air carries a lot of energy, a lot of moisture, and a lot of pollutants. If we have greater control and predictability of that airflow in and out of our house, then we can lower the conditioning cost of that air, the cleaning cost of that air, and have better assurance that the moisture that's being carried by that air isn't going to cause problems in our homes. Now, the other difficulty we have is that there are certain pressures that are exerted on our houses that we have little control over. That would be wind and stack effect. And then we also have pressures that are created by mechanical systems in our homes that can create problems as well, but we have a little bit better control and over those mechanical features that are put inside our houses. So from a wind perspective, we see that on the windward side, we get a positive pressure. On the leeward side, we get a negative pressure. And we get a pressure difference across the inside of our home as well here. So if we have the wind blowing on the windward side, we might actually be sucking air out of our house on the leeward side, when we might be pushing air into our homes on the windward side of the house. Remember that this air could be carrying moisture, heat, and pollutants. So it could be creating problems when that air moves across the building envelope, and it might be depositing, let's say, moisture and heat within the building envelope and creating condensation and repeated wetting, for example, inside that building envelope. So building our houses tighter can help resolve this issue so that we get less pressure difference across that assembly. In the same way, stack effect describes what happens to air as it warms. When air warms, it rises. And when it rises to the highest surface of the house, in essence, it's seeking a hole to the outside. And if it finds a hole and it leaves the house, then it's going to leave on the high side, pressure side, and air is going to be sucked in on the low side of the home, on the negative pressure side of the home. So again, if I build a house that's tighter, I'm going to have less air transfer that's happening just by stack effect or air rising because it's carrying heat to the higher surface of that house. Now, mechanical systems and the pressures that are created here are described by unbalanced ventilation systems, unbalanced HVAC systems, where I might have more supply in a room than I have return, or I might have more supply in a house than I have return in the house. So I have that house blowing up like a balloon because I'm pressurizing the house with greater supply volume than return volume. Or I might have a large kitchen hood that's exhausting 1,000 cubic feet of air from that house, but I don't have air coming back into the house at the same rate. So I have a negative pressure created by that fan. So mechanical leakage in our homes is generally being described by fans that are moving air within our homes or in or out of our homes that aren't balanced there. So we're always looking for balanced ventilation and balanced HVAC systems from a supply and returns perspective there. Okay, so what we've learned here is that airflow needs a hole and a driving force. If either is missing, then the air won't move in or out of that house. But we do know that if air moves into that house, it also has to push some air out of the house, or if air goes out of the house, air must go into the house, and that we measure air in cubic feet. And generally we measure it in cubic feet per minute going in or out of that house. And a cubic foot of air is about the size of a basketball here. So just to reiterate that. Now let's talk a little bit about infiltration and ventilation here. Air leakage is described by infiltration and exfiltration. So infiltration is this unintended, accidental, and often random movement of air in and into or out of our, well, infiltration is air moving into our buildings. Exfiltration is the same thing, this random, unintentional, accidental movement of air, but it's air moving out of our buildings instead of into our buildings here. Now, the infiltration load is accounted for in our HVAC design process, and we measure this infiltration load by using a blower door. So if you have a builder that's doing blower door testing, it's best to get an average of their blower door test and use that in your HVAC heat load calculations rather than an assumption, because the assumptions are not very accurate. In essence, they're using tight, semi-tight, leaky, very leaky as the assumption that you're using in that equation. And the actual numbers behind that tight, leaky, very leaky word inside the HVAC calculation is not very accurate there. So it's best to use the actual numbers measured by the blower door numbers. So we're ultimately trying to get control and predictability of air leakage by building our houses again as tight as we can. This will control infiltration and exfiltration. Now, mechanical ventilation is a little bit different, because in mechanical ventilation, we actually do have control and predictability. We know exactly the rate or the cubic feet per minute that the air is going in or out of our houses when we're ventilating it. We set it on a schedule and we know how much air is coming in at a 24-hour period there. We also know, so we have control because we know the rate, and we have predictability because we know the schedule. And we also know that this ventilation load is accounted for in our HVAC design process there. So the main reason we're trying to bring this out into the open ultimately is because sometimes the ventilation load and the infiltration load are conflated, especially when you're using exhaust or supply ventilation. Exhaust and supply ventilation is a specific ventilation type that is mechanically taking air in or out in a controlled and predictable way. So you want to take that load separately from the infiltration load that is random air movement through holes in our building envelope here. Now, ventilation systems are interesting because you can also tag some additional things on. You can ensure that you know where the ventilation is coming from a specific source, and you can filter and distribute that ventilation air depending on the ventilation system that you're ultimately installing in that house. Now, the primary function of ventilation is to provide fresh air for the occupant of that house, because we do want to build our house tight and gain the predictability so that we have better predictability of airflow, thermal flow, and moisture flow inside our houses. But we also need to ensure that we're getting the proper air for the occupants. And then we have background moisture control inside of our houses with ventilation systems as well. So to create that comfortable, efficient, and well-performing houses there, we want to ensure that we right-size our equipment, that are balancing all these loads in our houses, and that we build our houses tight, and that we've clearly defined that building thermal envelope inside our homes. If we have an undefined building thermal envelope, we're not going to be able to meet the core expectations that people have of their houses, and our design criteria will not work. So the code is actually helping us in this equation because it's making us clearly define the building envelope and depict that using a red line, blue line, yellow line thermal depiction test on our construction documents. It also clearly defines the building envelope as an assembly of things, and it defines in other areas what an air barrier is, and that we have to have the continuity of that air barrier system all the way around our house. So this air barrier system, if we simplify it, we know that we're talking about an assembly of things that are creating an air barrier in our thermal barrier. So interior drywall, for example, and the continuity of that drywall all the way around our house, adjacent to the thermal barrier of our house. That's what we're trying to get here. And the code basically says when that interior drywall is not continuous and not in alignment with the thermal boundary of the house, you have to add additional supplemental air barrier systems on the interior of the house. We most often see thermoply as that additional air barrier system, and that thermoply being added behind a tub on an exterior wall, or in an HVAC chase, or in a drop ceiling on an exterior wall, or behind a fireplace on an exterior wall, where the interior drywall, the aesthetic part, is not going to be in alignment with the thermal boundary here. Similarly, on the exterior of our house, our exterior sheathing is our primary air barrier system. And when we don't have that air barrier alignment, we're asked to, by the code, to get a supplemental air barrier on the attic side of a knee wall, for example, on the exterior of our houses here. Now, some might ask, what is the drainage plane or house wrap then? And the house wrap is that drainage plane. It can be a supplemental air barrier, but that house wrap generally is not installed well enough to actually be a supplemental air barrier there. So we're really asking for belts and suspenders approaches when we're talking about the IECC and our best building practices here. Now, the function of this air barrier system is to enclose the insulation to trap pockets of air. So that's when we talk about six-sided enclosed or closed insulation in our floor systems and our cavity wall systems, potentially raftered ceiling systems there. But it's only when we're talking about cavity insulation do we talk about enclosure, so that we can get better air control, thermal control, and moisture control in our houses here. Now, this is from an air perspective. When we're talking about thermal control, we need to ensure that we're installing our insulation in accordance with manufactured instructions. That's the main installation instruction that the code is looking at. And it specifically says it in the code here. We get other installation criteria within the body of the code, but all insulation, all fibrous insulation that's air permeable needs to be installed properly so that it actually functions. So air permeable insulation works just like insulation works on our body here. So this person has a fleece jacket on, and the object of this fleece jacket is to trap a pocket of air. Now, the other thing that has to happen for that fleece jacket to work is that that pocket of air needs to be a stagnant pocket of air. It can't be moving in and out of the insulation material, in this case, fleece. But it really doesn't matter if it's fleece or cotton or wool. The object of that insulation is to trap a pocket of air. And that's the same thing that's true for fiberglass, cellulose, foam products that are in our houses. Though the object of that insulation in our home is to trap a pocket of air, and it's that pocket of air that resists the flow of energy from higher concentrations to lower concentrations. So in this case, with this fleece jacket, if this person walks out on a windy day, the pockets of air are moving in and out of the fleece jacket. So we know to put on a nylon shell on top of the fleece jacket in order to get an air barrier and in order to increase comfort and reduce the amount of heat loss from our assembly here, which would be our body here. So if we can stop the movement of air pockets and we can get a system, we get a system that actually works here. So she has an interior air barrier, which would be her skin. She's got a fleece jacket, which would be her insulation. She's got a nylon shell on the outside, which would be her exterior air barrier. And she's got a system that actually works. So in our homes, it's really the same. We've got insulation inside of our cavities that resists conduction, but it doesn't resist airflow and the energy moving with air. So we need to put that insulation within a cavity, a six-sided cavity here. When we talk about insulation that's in a ventilated attic that can't be enclosed inside of a six-sided enclosure, we're talking about compensating by the depth of installed insulation for our inability to enclose it on that top side, that ventilated attic side of the equation. So we know it would work better, but we can't do it. So we're just going to add more insulation so that less of the air is going to move through that insulation and degrade its ability to work. Because one of the biggest myths about insulation, especially fibrous insulation, is that it stops the movement of air. So going back to the code real quick, this table helps us gain control and predictability of airflow, which helps us gain control and predictability of thermal flow and moisture flow as well. It does it by telling us different sections or areas of the house that we need to deal with, how we install the air barrier systems around that, and how we also install the insulation that's adjacent to that air barrier system, and how do we get continuity all the way around our building envelope. We have to remember as well that there are other sections of the code that talk about insulation installation. This is talking about the coordination of the air barrier and the thermal barrier insulation. And so if you follow this table well, you should not have an issue achieving the air tightness requirements that are required by the IECC now and measured by blower door testing here. So in our HVAC design process, we know that we're trying to determine how much energy load is coming into our houses in the summer season that we're going to have to condition and cool, and how much energy is leaving our houses in the wintertime condition that we're going to have to replace and heat and cool as well. So we have to properly size our houses, which means that we can't use assumptions to do that. We want to use the accurate R values and U values in our heat load calculations. And we want to actually do proper ACA approved heat load calculations in order to get the right sized equipment inside our houses. The manual J is that load calculation. It ultimately doesn't tell you the size of the HVAC equipment. The load is how much heating and cooling the house needs. The capacity of the heating equipment needs to be chosen properly so that the equipment has the capacity to meet that load there. So often the equipment's capacity is going to be slightly bigger than the load so that we can work through squeaking seasons and that we can work through efficiencies of equipment. But we ultimately want to ensure that we have enough capacity to meet that load and that our systems aren't going to be oversized or undersized. So when we talk about assumptions, we have to not only think about the assumption of what R value we're designing to. So let's say I'm designing to an R19 bat, but we have to overcome the assumption that that R19 bat is going to be installed properly and we're going to get that R19 bat in that cavity correctly. So in this case, the bat wasn't installed properly. So if I've got performance in the R4 range or R7 range, my system isn't going to match my envelope and my HVAC design isn't going to work. So we need to make the proper assumptions for our building envelope. We need to verify our building envelope, and we need to right size our equipment to ensure that we're going to get systems that ultimately work, which means that this fundamental question needs to be added to our inspection process, either by third-party inspection or with our code officials. Is it there? And ultimately, yes, this installation's there, but the second question is, has it been installed so it's actually going to perform and work? Is my thermal envelope going to actually work? Is it going to match the assumptions that the HVAC contractor has made? And can I ensure that that contractor, that he doesn't have to make an assumption to oversize the equipment for the poor envelope that he thinks he's going to get? The reality is that the envelope has gotten better and better. We're doing more and more good inspection and assurance that it's working. We also need to do that on the air side of the equation. So we've got the assumption here that I've got a good exterior air barrier system on this house. What about the interior air barrier system? Because remember, the thermal envelope, a building envelope is an assembly of things. So I have to have an interior and an exterior envelope and air barrier system here. So we rely on blower door testing to test the building envelope. We rely on duct testing to test the continuity of our duct systems there, and all these things working together. So to conclude, we have an HVAC design process that is intricately linked to the ability of us to execute on that building thermal envelope. We need to think about using design integration meetings to bring all the players that are building that house together early in the design process so that we can ensure HVAC performance, we can ensure envelope execution and envelope performance, and we can ensure that these systems are going to work and work well for the objectives of that particular house. We want to ensure that we verify our houses, verify the performance of those houses, verify that we get control and predictability of airflow, thermal flow, and moisture flow in our houses so that we have houses that are durable, are efficient, and are safe for the occupants of those houses that we're working on here. So thank you so much for taking some time today to discuss these topics. Remember that you can register for other seminars that are coming up. The next seminar is about manual J calculations specifically. The next 3 are all about HVAC design. We'll be talking about manual J on December 2nd, manual S on December 9th, and manual D on December 16th. I'm happy to stick around and have a dialogue and answer any questions or just talk more about this, or you can reach out to me specifically at my email address or on Instagram at Build Tank Inc.
Thanks, Robbie. Yeah, so we're a little bit over on time today, but if anyone does have any questions, feel free to either raise your hand or type a question into the Q&A box. We are doing next week for Thanksgiving, so I hope everyone has a happy holiday. But we'll start back up on December 2nd. So Robbie, just to start off a question. I mean, in your field experience, what areas are often neglected that kind of contribute to the occupant comfort that you see like the most in the field, I guess?
On a thermal envelope perspective, insulation in floor systems often is not done well enough, especially if it's a batted system instead of a blown system. In general, blown products work way better than bat systems. So if you have a batted house, your inspection process and verification process of that thermal envelope just needs to be significantly better than if it's a blown product. On the HVAC side, we're still seeing some really leaky ductwork because the code only requires us to test a duct system if there's a portion of that duct that's outside the building envelope. And it doesn't mean that you're not going to have an unbalanced system. You're not going to have extremely leaky ductwork if all that duct is inside the building envelope. So I tested a house the other day, about 700 CFM of duct leakage in that system, all of which was inside the building envelope. It means that the conditioned air isn't getting to the right places, that people are probably going to spend a lot of time adjusting the thermostat and using more energy because they're going to try to they think that they can get more heat or energy to those cold areas of the house there. So those are some of the things that we still are trying to address better.
Yep, definitely. That makes sense. We do have a hand raised here from Patrick Hunter. I'm going to go ahead and allow you to talk, Patrick.
Thank you. Hey, great talk, number one. Two, have you ever worked with Joe, is it Sturbick?
Sturbick, yeah.
Is your organization any connected to him in any way?
We are just colleagues, and we talk a fair amount, but we're not corporately aligned, I guess.
Cool. What about spray foam on walls?
Now, spray foam is a great product. The one thing I believe in is that a number of builders in particular believe that spray foam is a panacea that's going to solve all their problems and issues. We have to realize that spray foam is primarily sprayed inside of a cavity, and most of the air leakage of our home doesn't happen inside of the cavity. It happens where different things are connecting together, like the sill plate to the foundation or the bottom plate to the subfloor, for example. So, and then the other issue is understanding that spray foam is introducing a specific R value into your cavity, and that R value is measured by the inches of material that you're installing, and that air tightness is measured separately by the blower door. So some folks that are selling spray foam products that are insulating your houses are conflating air tightness and R value, and those are two separate things. And so when they tell you an equivalent R value, you should ignore that and say, what's the actual R value of the install? Are I want an R 15 in my wall, then therefore I need what, 2 inches of material or whatnot. You won't want them to say, well, I am going to install 1 inch of material and it's going to perform like it's an R19. 1 inch of closed cell foam is only about 6.5 R value. So those are some of the things that we need to just keep in mind when we're using spray foam insulation products, Doesn't mean that it's a bad product. It's just that it doesn't solve all our issues.
What about air exchange equipment? Heat exchanger, air heat exchanger equipment.
What's the question about that?
Is this almost universal now in new homes?
I think you're actually talking about ventilation equipment.
Yes.
Okay. Yes, it's a mandatory requirement of the IECC. You have to ventilate your house. Now, how you do that, you still have a lot of options, and those options are very dependent on your climate. In Colorado, we're lucky because exhaust ventilation, supply ventilation, and balanced ventilation, the three strategies to ventilate your house work well in Colorado. But if you're in a humid climate or a really cold northern climate, you might choose to only use balanced ventilation because you have more control and predictability with a balanced ventilation system. But the big thing to know, if you didn't know, is that it is a mandatory requirement. And yes, these systems are being installed into new homes now.
Thank you.
Yeah.
Thanks, Patrick. All right. I think that's all the questions that we have for today. Thank you again, Robbie, for your in-depth presentation. You covered a lot of topics that I know has been asked about in our surveys and everything. So have a happy Thanksgiving, everyone, and we'll see you in just a couple of weeks.
Great. Happy Thanksgiving, everyone. Be safe.